So today's topic will be more tailored for geotechnical engineers. It will be soil pile interaction. And actually it will be based on a topic that came up on our forum by Dr. Bence. It is among the attendees. What is your name? Did I pronounce it properly? Bence? Yes. Okay. Yeah, I'll be doing a model very similar to the one that you did on our forum. And I also found the reason why it was crashing sometimes when you change the elements. So I will explain it today and how to parallelize it. So how to do the same model with OpenSees MP. And I will show you that with OpenSeesSP it doesn't work. So basically what you had to do to avoid the crash was to remove the load from the hole before removing the hole. Okay, and I will go through that topic. We still have some more attendees joining. Okay, we have 30 attendees more or less. As usual, you will find all the materials and the video recording by tomorrow on our website. And for all of you, we just released STKO version 2.0.3. So you can upgrade it. There are some new features that are quite useful. Okay, so I think we can start. So once again, welcome to this new webinar. Today's topic is soil pile interaction. So how to do soil pile interaction in STKO and OpenSees. It will be, actually there are several ways to do soil pile interaction. We will be doing a full 3D model for the soil, and the beam will be the column, the pile will be a beam element. And I will show you also how to use contact elements between the beam and the solid domain, and how to perform excavation, so how to remove the solid before putting the pile inside. Okay, so I'm going to share my screen. Okay, here we are. I'm going to full screen. Okay, so before we start, I will show you how it will look like, the folder that you will see tomorrow on our website. So these are all the contents. They are all the same model, okay? First, I will start with a simple model called soil pile custom TCL, and I will show you why we start with that. So we start with this one. The geometry is the same for all the other models, okay? There are just some small changes in the analysis settings for parallel or sequential analysis. So this is how the model looks like. You will have a solid domain. Now to make this model quite fast, I modeled just a small piece of solid, okay, just to show you the main concepts. And there is a beam inside, okay? So this pile is actually a beam. This one is the extrusion, but if you look at the geometry, it is a simple line, okay? So actually the geometry is pretty simple. You have a solid domain here, and you have a pile. So if I select this one and I hide it, you will just see a pile here, a beam column element. Then you have the solid domain, and you have an interaction that will be used to connect the pile to the faces of the solid domain, and this interaction will simulate the contact. Okay. Then another thing that you have here is a cylindrical local axis. We will need it because this kind of contact element, I will show you later on what is the contact element that we are using, needs a coordinate transformation to understand what is the direction of the beam. Okay, so I just used this cylindrical orientation in such a way that when you assign this one to this interaction, all the interaction will have a coordinate transformation that follows this linear coordinate, this cylindrical coordinate system. Okay. Now all these models will be pretty equal. Oh, the mesh is not very fine, just to make the model pretty fast. Just a simple note: if you want to make sure, if you want to model your solid domain with hexahedra element, okay, so 8-noded bricks, you need to make sure that your solid is capable of being meshed using a structured mesh. Okay, and to do so, you have to make sure that every solid here inside this composite solid domain is made of 6 faces. Okay, that's why when I created this geometry here, I needed to create a hole here with a cylindrical section. Let me go to geometry so you can see it better. So this one is a cylindrical section, is a circular section. And to make sure that each one of these faces can be meshed with a structured mesh, you need to divide it. Okay, so the construction of the solid was quite simple. I started with creating the boundary lines. Okay, then I created these intersections here, and I just used the planar command and selected all the lines here to create these faces. Then I took these faces and I performed 2 extrusions. Okay, 20 meters for the 20 meters of pile inside the soil, plus another 10 meters, I think, just to not to put the bottom of the pile directly to the ground. Okay, so I put a little bit more solid here. Yes, it was 20 meters, another 10 meters. And then the pile is outside of about 2 meters, yes, other 2 meters. So 20 meters inside, 2 meters outside. Everything will be in Newton meters, so the international unit system. And as I always say, be consistent with your units, okay? Because I often, on our forum, I often see errors about inconsistencies between the units used for length, forces, and masses or acceleration, okay? So always try to be consistent. So as I said, the geometry is pretty simple. We just have one line and a composite solid here. Then we have 2 interactions, actually, not just one. Let me show you. One interaction is called pile soil side interaction, which is basically this one. Select is the interaction between the whole pile and the faces of the solid domain. Okay, so this faces here of the hole. This one is to simulate normal and frictional contact between the pile and the hole here. Then you need another kind of contact, which is the one at the base. Okay, so to simulate the contact between the pile toe and the base of the hole, which is this one, pile soil bottom interaction. Both of these interactions are similar in the sense that they are a node to element link, okay, where basically the master, or actually the retained node, are those of the beam. Okay, so you should select the beam as master and the solid faces, now the vertical faces of the hole or the bottom of the hole, as slaves. And for this reason, I created several selection sets. Okay, so it can be easier for selecting. Let me show you just the selection set to understand why we need them. So whole vertical faces, select. It contains just the faces. Okay, so not the entire solid, just the faces of this hole. Okay, I will need it to select them when creating the interaction. Similarly, there is another selection set which is the whole bottom face. So selection set containing the faces at the bottom. Okay. So also this one is only useful for creating the interaction. Then you can get rid of it. Then we have another two selection set for the solid domain. Why do we have two selection set? Well, one is for the entire solid domain except this part in the middle. Okay. Why? Because we are going to remove the solid portion which is inside before putting the pile there. Okay. So we'll simulate actually a construction stage. So the solid domain, the soil domain is the entire soil domain except from this central hole. Then there is the whole domain, okay, which is this one instead. Then we have the selection for the pile. We will need them because we are going to add pieces one at a time, okay? So to simulate the construction stage. And we also have a selection set for contact elements. So this selection set contains both these interactions. And finally, we have a selection set for the top node, top vertex actually of the pile that will be used for the displacement controlled analysis. Okay, so just to apply the displacement in the displacement controlled analysis. So here we have the selection sets, the geometry, and the interaction. Okay. Now for the definition, we just have a linear time series because we are going to do just a static analysis, and this linear time series will be used for both vertical analysis, so gravity loads, and for the subsequent displacement controlled analysis. Now about the materials. I created everything in such a way that it can be converted into a nonlinear model, okay? But now I want to focus on the modeling part and the contact part. So I only used elastic isotropic materials for the soil, and an elastic section for the beam. But as you can see, I didn't use an elastic beam column because in this way, for example, if you want to test a nonlinear beam or a beam with fiber section, you just go here, you change the elastic section into a fiber cross section, and you're ready to go. Okay. So the elastic soil was an elastic line, okay, Newton meters. And actually here I added the mass density, but it is not important because we are going to do static analysis. Then we need a contact material. This contact material will be assigned to the interactions, okay, because the contact elements that we are going to use, they need a contact material. This contact material is an instance of contact material 3D, and it requires just 4 parameters. Okay, so 2 of them are mandatory. These 2 can be set to 0. What is the meaning of this? So this one is the friction coefficient, which is basically the tangent of the friction angle. Okay, so if you remember the, let me do a drawing. Okay, so if you have here, you have the normal stress, so sigma n, and here you have tau. This one follows a classical Moore-Coulomb rule. Okay, so basically, mu is the tangent of this angle here. Okay, and g is the stiffness parameter. Okay, now actually, it really depends on what you want to model, but in this case, I use the same g as the shear modulus of the soil domain. Actually, to be more consistent, you have to use a value that is quite higher because you want it really depends on what you want to model. Okay, so if you have just a zero length contact interface, it should be a very large value, almost infinite. But if you use a very large value, it will give a lot of convergence problems. Instead, if you want to simulate a cohesive part of material that has a finite stiffness, so you can use that one. Then you have C and T. C is the initial cohesion. This one is 0 if you want to just to model hard contact. So you have the pile, you have the solid, but in between you don't have anything. Okay, so there is no need to put a cohesion. But what is a cohesion? Well, if you have a cohesion of C, the cohesion is the intercept here on this line. Okay, so if you put a cohesion of 2, and this one is 2, for example, your yield surface will be like this. Okay, And so basically, instead of starting at 0, you will have a just an extra part of yield surface. But physically, it means that there is a material between the pile and the soil, okay? But in our case, there is no material there, so there is not a cohesive zone. Why? Because, for example, if you are in a tensile stress, so it means that the soil is detaching from the pile. If you have an initial cohesion, then there will be a resistance in shear. But if you have hard contact and you have separation, there will be no resistance in shear. That's why I put 0 here. And then you have T, which is a tension cutoff. For example, if using this cohesion, the tensile strength coming from the cohesion and the slope of this line is too large for you, you can put a value that can be something like this, okay? So you can put a tension cutoff. So this one will not be considered, okay? But as I said, I'm going to, just to represent hard contact, so no cohesive zone in between. So this one will be my yield domain. If the stress state is inside this yield domain, it means that I have a stick condition. So the pile will move together with the soil. As soon as the tau, so the shear stress, is larger than this yield surface, so it is here, for example, there is the plasticity. So this one will be returned onto the yield surface and it will be a plastic slip, okay? Perfect. So this one is just the basic of about the Mohr Coulomb friction law. Perfect. So that's why I use C equal to 0 and T equal to 0. Perfect. So going forward, we have to assign properties to the pile. As I said here, I just want to simulate an elastic model. So I have a circular cross section, a full circular cross section of 1 meter of diameter. And then I have a Young modulus and G modulus of concrete. Then we have the pile property. As I said, I decided to use an elastic section and a beam section property because in this way the model is elastic, but it is ready to be changed into a nonlinear model. Okay, so you can just change the elastic section into any nonlinear section. So pile property is just a simple Lobato integration rule using the elastic section as section and 5 integration points. And then we also have another material. I don't know if I've ever talked about this one before, but this one is called initial state wrapper. Why do we need this one? Well, first of all, it is very simple to define. So you go under materials and D, and then you have wrapper material for initial state analysis. And this material basically just wants the index of the material that should be converted into an initial state material. So in our case, it will be the soil domain, soil material, and the number of dimensions. So 2 for 2D analysis or 3 for 3D analysis. Now in our case, we are doing a 3-dimensional analysis. What this material is going to do. So this one is basically, when we are going to perform the analysis, okay, at the beginning, we only will have the soil domain. We will apply the vertical load to the soil domain. And the soil domain will deform, okay? But then in a second stage, we want to add the beam. The problem is that at the moment we add the beam, the soil domain will already have an initial displacement. So the beam will be incompatible with this initial displacement. So in order not to have this kind of problem, in OpenSees, we can use the initial state analysis wrapper together with a command which is called initial state analysis on and off, that basically brings all the displacement to 0, but keeping the stresses, okay? So basically what you will see is that the model will go down due to gravity loads. It will develop an internal state of stress. And then it will be, the displacement will be reset to 0, but the stresses inside the soil will be kept, okay? So it will be, this one is very useful for doing staged analysis while keeping the stresses coming from the gravity loads, okay? So that's why we need to define an initial state wrapper. Okay, so once we are done with physical properties, we need to define the element properties, okay? Now, for the soil domain, I just used a reduced integration brick element, so a single point integration. For the pile, I used a displacement beam column. I didn't need a force beam column because in any case, as you will see from the mesh, the pile is being discretized, okay? So there are many pieces of pile, so you don't actually need a force beam column here. Now, in this case, this one is an elastic beam, so either displacement or force beam column is the same. And then you have other two contact elements, which are the beam contact 3D and beam end contact 3D. Now, actually, in OpenSees, there are two variations of the beam contact. The standard one and the one that ends with P, okay? So there is this one here. Actually, if you go on the documentation, there is no documentation online for this one, beam contact 3D P, because it has been added, but there is no documentation yet. But basically, the concept is the same. So you can see the documentation for the standard. This one is OpenSees beam contact 3D. You can look at the documentation for this one, and the beam contact 3DP actually works in the same way, but it enforces the contact in a different way. So the beam contact 3D basically wants its own tag. Then the two nodes, the retained nodes for the beam coming from the beam, okay? So that's why these nodes should have a dimension of 3 and 6 doves. Then the constraint node will be the constraint coming from the solid. That's why 3, 3. And then you have an extra node called L node, which is the node with the Lagrange multiplier degrees of freedom. Because the original version of this kind of contact material uses the Lagrange multiplier to enforce the contact condition. This one can create a lot of problems. It's also described here because the Lagrange multiplier actually puts the contact forces into the solution vector, so inside the displacement. And it will be a mess whenever you try to do the test, the convergence test. Then all the others are the same meaning. So they have you have a radius, because this contact element wants to know what is the radius of the pile in such a way that he knows when there is contact or not. The coordinate transformation of the pile, that's why here I had to assign a coordinate transformation to the interaction. And here it wants just two tolerances, which are not present in the version that we are using. I decided not to use this one because Lagrange multipliers are somehow tricky to use. So I prefer to use the penalty version of this one. So the element that I use, basically they follow the same concept, but the ones finishing with P at the end of the name, P stands for penalty, because actually there are two ways of enforcing a contact condition. Either the Lagrange multipliers, but the problem is that it requires extra degrees of freedom. That's why they need an extra Lagrange multiplier node. And working with Lagrange multiplier is quite a mess. So I decided to use the penalty approach. The penalty actually requires this extra parameter, the penalty parameter, which is actually a stiffness. And what is the meaning of this stiffness? Well, actually, this stiffness parameter is used to enforce the stick condition, as I said before. So when you are inside the yield surface of the Moore Coulomb friction law, there should be no relative displacement between the beam and the solid, okay? So they are in stick condition, so they should move together. Now, to enforce this kind of condition, you need a penalty parameter, which should be infinite, okay? So if you have an infinite stiffness, you have a zero relative displacement between them. The only problem is that you cannot use an infinite number, okay? So it means that you should use a very large number. But this also creates another problem. If you use an extremely large number, you have problems in the conditioning of the system matrix, okay? So imagine that your entire stiffness matrix has stiffness coefficients of the order of 1 to the power of 6, and then you put here 1 to the power of 20. Now this number will be extremely much larger than all the others, so that all the others will be seen as 0. Okay, that's why if you put extremely large number into the stiffness matrix, it will be singular. Okay, so how do you calibrate this number? Well, what I do actually is to estimate the stiffness that I have in my model, and I put a couple of order of magnitudes more than that. So for example, in my model, I have a Young modulus of 6, okay? So this Young modulus will be multiplied by the volume or the area or the length, whatever it is, of the element. Now these elements, since I'm modeling in meters, they have a characteristic length of 1 meter. So the order of magnitude of volume is 1. So this stiffness will also have a order of magnitudes of 6 times 1, so 6. So 3 for order of magnitudes is fine. That's why I used 1 to the power of 10. Okay. So try to do, it should not be a precise number, but just try to estimate what is the stiffness in your model and use 2, 3, 4 order of magnitudes more, not too much. Okay. So this is fine. And then there is another topic here. Oh, well, you have to specify what kind of geometric transformation you want to use, and it should be the same as the one that you use for your beam. Okay, so in my beam, I use the linear transformation. So here I use a linear transformation too. Okay, so if instead you want to put nonlinear kinematics, like for example, corotational, you put corotational transformation to the beam and also here. Then there is the radius. As I've seen before, the pile section has 1 meter diameter. So here I should have put 0.5. But actually there is a problem if I put exactly 0.5, because since there can be some round-off errors between the coordinates of the nodes coming from the solid and this 0.5 here, it may happen that OpenSees sees that some nodes of the soil are actually inside the beam, so they will start like in a stick condition. So that's why I put a value that is quite close to 0.5, but not exactly 0.5, okay? And here I also said that by default, they start by saying that they are in contact. But here I said, no, I don't want them in contact, because if you switch this off, the result will not change that much, but you will see that the nodes from the solid will start detaching little by little, but actually at the beginning, they are not attached, okay? So that's why I used the C switch. And then there is the contact at the bottom. Also here, you have to specify the same penalty number and the radius. Now here I did the opposite. I made the radius a little bit larger. Why? Well, let me do a drawing so I can explain this one. Therefore, stop here. Okay, so now imagine that this one is the bottom of the soil, okay? So I have, for example, 3 nodes here. And this one is exactly 1 meter, okay? Then here I have the node of my pile, so the pile toe. And I assigned a contact material here, connecting all these nodes with the bottom of this pile here. And then I said that my radius is 0.5. Now what happens to this node? This node is exactly at 0.5, okay? But if for some round-off error, this one is slightly larger, okay? So even 0.50001, it will fall outside the beam, okay? And so this one will not be in contact. That's why I decided to enlarge a little bit the radius. So I said the radius is 0.5 plus a small tolerance, and also here, so that I make sure that these nodes will detect the contact, okay? So when you assign the radius at the bottom, you put some small tolerance, you add some small tolerance, and on the side ones, I remove a small tolerance, okay? The penalty stiffness is the same, okay? Actually, in all this analysis, this one, the beam and contact is not going to, by the way, check the name is slightly different, beam and contact 3D, because it uses a different approach, okay? So this one is the contact element that you should assign to the pile toe, while the beam contact 3D is the one that you should use for the side nodes. I think we have a question here on the chat. IUA. Does the beam contact 3DP require us to use cylindrical local axis? Actually, they don't, because actually, for me, the cylindrical local axis was the only one useful for assigning an x direction going forward. So you can actually assign any local axis that has an x direction going upward, okay? So the only important thing is that the x-axis of the local axis coincides with the direction of the beam, okay? Why did I decide to use this cylindrical one? Well, because I will use this kind of example later on in new webinars to assign different kind of contact elements. And the new kind of contact elements, they will need a cylindrical local axis, okay? So for this specific one, it is not necessary. The only important thing is that the x-axis points in the same direction of the beam, okay? But I will use it for next webinar. So that's why I decided to use the cylindrical local axis. And as you can see, the cylindrical local axis is actually pointing, well, actually here it's pointing the y direction, but when projected onto the beam, it will point, actually it will point, the necessary thing is that the z direction is coming outside, because then it takes the x direction from the direction of the node, okay? So the only important thing is that the z is going outside, and the cylindrical one is the only one that guarantees that the z local axis will go outward. So let me do a zoom here, and let me hide this one. If I switch on local axis, you will see that the z is always pointing outward, okay? Actually, if you put the x on the vertical direction or not is not that necessary, because in any case, it can take the x direction from the beam, okay? But the z direction, it cannot be taken from the beam, because it can be any axis rotating about the x-axis of the beam. So you have to specify it, okay? So this is the only requirement. Okay, let me switch this off. Okay, here we are. Contact bottom, perfect. Now we need the boundary conditions. Okay, so we have everything here. We need to specify boundary conditions. So first of all, we have to put some fixities at the bottom of the soil domain. And here I decided to fix the entire, all the phases in all the 3 degrees of freedom. And then I fix the x and y. So I put a kind of plane strain condition. The x and y, so the x displacement will be applied here, but you can use any other kind of boundary condition, okay? So this one was useful only to simulate a small piece of volume. So there is no x displacement in these two vertical sides, and there is no y displacement in the other two vertical sides, okay? So these two here, front face and back face. Then we need to define the gravity loads, okay? So for the gravity loads, we need to specify the self-weight for the soil and for the pile, okay? So the pile will be an edge force. So if I edit it, I have the specific volume times the cross-sectional area. So it becomes a load per unit length. And this one is assigned in global direction in the negative z direction to the pile. Okay, so this is pretty simple. And then the self-weight for the volume needs to be a volume force. Okay, so it should be assigned as a specific weight actually. It is this one. This one and this one, they have the same value applied on the negative z direction. And then you may ask, why do I need two of them? If they have the same value, I can simply create one of them for all the entire soil domain. While here I'm using a self-weight for the outer domain, so the soil domain that remains into the analysis. And then I use a different, but with the same value, a different load in the inner part of the hole, because this one is the part that is going to be removed. So why do I need to do this? And here I'm referring to Dr. Benson. This is the reason why you had a crash in your program. The problem is that when you remove an element, oh, by the way, I'm going to remove these elements during the analysis, okay? So if you remove an element, and of course you have to remove also these floating nodes that remains here. If you remove elements and nodes from OpenSees, you have to make sure that you also remove nodal nodes, okay? Otherwise, when you do the analysis, there will be some nodal nodes referencing a node that is not in the domain anymore. And OpenSees will simply crash, okay? Because there is no way for OpenSees to do a check if a node is still there or not in the way they implemented it. So if you keep the load on a node that has been removed, it's likely that you're going to have a crash. So in order to do that, I need to be able to remove the load first in the hole and then remove the element, okay? But to do so, I need two separated volume forces, one for the outer domain and one for the inner domain of the hole, okay? So this is the reason why I created two separated volume forces. And then I need an horizontal force applied here at the top, okay? Actually, this one can be a unit value or any other larger value, is not important, because actually this will be displacement control, okay? Applied here at the top of the pile, okay? Okay, so and then we start with analysis steps. So this is the hard part. Basically, what you will find here will be very similar to all the other examples that I will show you. There are just some small differences. So the first one, we have something in the chat. Mense, I see. So I guess that's why every time I try to change around the model for a more physically correct scenario, the simulation failed. Yes, that's the reason. Actually, since OpenSees does not check if a node exists or not when it applies the load, it may happen that when you have a few nodes, there is a memory corruption, but it's so small that the application doesn't crash. When you increase the number of nodes, then this memory corruption takes more space and it can lead to crashes. But it can actually also lead to wrong results. The problem is that whenever you try to write to a memory space that has been removed, you cannot predict what the result will be. It can make a crash or it can simply create random results, okay? So this was the reason why you had crashes. Okay, so now all the steps that we need to perform: a gravity load of the soil, excavation of the hole, putting the pile, then doing the settlement of the pile, and then applying the horizontal displacement is summarized here. So the first thing that you need to do is to create a recorder as usual. Then, since we need to do a staged analysis, I need to create the model subset, okay? So I need to put pieces of the model one at a time. So the first model subset will be the soil domain. So I call this one add soil domain. So if you have never seen model subset before, it's pretty simple. You go under analysis steps, MIST command, model subset. And then in the model subset, you simply have to specify a list of selection sets that contains the element and nodes that should be applied in this specific time of the analysis. So see, this is the beginning. So from the beginning of the analysis, I want the outer soil domain and the whole domain. This means that I want the entire soil, okay? So at this first stage, I will have the full soil. Then I need to apply boundary condition to this soil domain here. Keep in mind now, I don't have the beam yet here at this point. So the constraint that I'm going to add is simply the fix at the bottom and the fix in X and Y at the vertical sides of the soil. Then I can apply the soil self-weight. And once again, I need to apply the soil self-weight in two separated load patterns. This is mandatory because in OpenSees, you cannot remove a load from a load pattern. You can remove a load pattern globally, but you cannot remove loads from a load pattern. So if I would have done something like this, for example, I use just one load pattern to apply both the self-weight of the soil and the self-weight at the hole, I would have a crash because I cannot remove this one inside a load pattern. But OpenSees allows me to remove a full load pattern. So I can do something like this. I create a load pattern with the linear time series and with the load at the outside domain, so soil self-weight. And then I repeat the same. So same time series at the same analysis time here, so before the gravity. But then here I use the soil self-weight of the hole, okay? So that I will be able later on to remove this load pattern before removing the soil domain. Okay, so once we are done, we need to do the vertical analysis, okay? But as I said, this vertical analysis will produce initial displacement and initial stresses. But I only want to keep initial stresses, not the initial displacement. I want the initial displacement to be 0. So the trick to do this one is to issue the initial state analysis on and then switch it off later on. So what you can do is to simply create a custom command that is basically a TCL script with a simple call like this. So initial state analysis on. It means that now I'm starting the initial displacement analysis. Then after this, I create a vertical analysis. Pretty simple. So static analysis, transformation method. This is a sparse solver. For contact, I prefer Newton with lens search, but you can try to test other solvers, other algorithms. Then I choose a non-displacement increment test, and here be aware to use a quite small tolerance, because when you have contact, the contact condition try to enforce the equality of the displacement between the two bodies, okay? So if I put a tolerance of 1 to the minus 4, and for me 1 to the minus 4 is allowed in the elastic slip, I will commit an error, okay? So I need to use a quite small number. So 1 to the minus 7, it should be fine. Then this is a load control. The first analysis is very simple because I don't have contact at this point. So just one increment to perform the entire analysis, okay? Because this one is elastic. I don't have any contact at this point of the analysis. So this one will be very easy. And then keep the load constant, because of course, then I want to keep the self-weight constant, and reset the pseudo time to 0, okay? Perfect. Now I need to remove the whole domain. Actually, this piece of code are taken from our forum, and this is actually what Benz was doing. So with the current version of STKO, okay, you don't have a tool to automatically remove a model subset. But actually, you can do it if you know a little bit of TCL scripting. So actually, now I will tell you how I did it using a custom command, and then I will show you how to create a new Python script, a new Python automation called remove model subset that will be available in the next version, but I will send it to you by tomorrow, so you will be able to use it. And with this tool, you will be able to do this kind of script actually automatic with a single click, and it will work also in parallel. I will show you in the next example. So now just to understand how the excavation works, I need to remove all the elements coming from the inner hole domain, okay? So how I did it? Well, first of all, I need a list of nodes that I want to remove, okay? So a list of elements that I want to remove. So I create a region, okay? Not because actually I need a region, but because the region command in STKO, other than creating a region, also allows you to write the list of elements into a TCL list, okay? It will be useful later on, okay? So basically I'm saying, okay, I want to create a region containing all the elements coming from this selection set here, which is the whole domain. So all the elements inside this hole, they will be written in a list called region remove, okay? Then I need another region actually, which is the region to keep, because actually, if I remove all these elements, and these elements contain also the nodes on this boundary, I cannot remove those nodes because those nodes belongs to element that will remain into the analysis, okay? So I need to perform a difference between two regions. So I need the region to remove that contains all the elements and the nodes that I want to remove, and then a region to keep. This region to keep will contain the nodes that should not be removed from this region. Okay, so for example, in my case, I created a region of type nodes containing these two selection set of vertical faces and bottom face of the hole. Okay, so basically what I'm saying, and of course I want to save the nodes of this selection sets into a list called region to keep. Basically what I'm saying is that I want to remove everything in this solid here except from the nodes on the boundary, okay, because I need to keep those nodes. Perfect. So once I have these two regions here, I can create, well, actually first I need to remove the load pattern, because as I said, if I don't do this, you will have a crash. So you can simply remove a load pattern and you use the model, remove load pattern, and you have to select here what is the load pattern that you want to remove. And of course, I want to remove the self weight from the hole. Okay, so before removing the element, remove the loads on that element, on those elements, and then I can perform the excavation. So there are two ways of doing this. In the current version of STKO, you can simply do it with a custom script, but the problem is that it requires a little bit of knowledge of TCL. Okay, so what I'm doing here now, without going into the details, I'm doing a loop on all the elements containing in the region to remove, which has been defined here, region to remove. Then I get the element nodes using this OpenSees command. So give me the nodes of the element defined by this tag. Then I remove the element. And then I remove all the nodes of this element if they do not exist into the region to keep. Okay. So basically this one is saying remove the element, remove all the nodes of the elements if they are not part of this region here, the region to keep. Okay. So once I do everything, I simply print something to the screen and I issue a domain change because something has changed in my domain. Now this one is it's not that complicated. The problem is that you need to know a little bit of TCL. But the problem is that this one works in OpenSees sequential. And changing the script for OpenSees MP, so for parallel analysis, is quite complicated. So I decided to create an automation for this that I will explain later on. Okay, so up to this point, I will be able to remove the solid inside the hole. Then I can perform the excavation analysis. Actually, this one is just a single step because now all the solid is down. I remove the place of the pile, and it will be a small redistribution of stresses. So also here, this one is very similar to the previous analysis. So static analysis, transformation, Newton, just one load step. Because once again, at this point, we are in a linear elastic stage. Once I'm done with this, I've done gravity and excavation, so I can switch off the analysis, the initial analysis. So that now, basically, with the initial state analysis off, which is pretty similar to the previous command, but it's simply initial state analysis off instead of on. So at this point, I perform my gravity analysis, my excavation, and after issuing this command, all the nodes will come back to a zero displacement, so to the initial configuration, but the stress state will be kept, okay? And that is the important thing that we need. So undeformed configuration, but with the initial stress of the gravity analysis. At this point, I can add the pile. Once again, I need to use another model subset, but this time it will contain different selection sets. One for the pile, and the other for the contact elements. So in one shot, I add the pile and the contact elements between the pile and the soil. So once I'm done with this, I can add the pile self weight. So once again, this one is a simple load pattern with a linear time series containing only the load or only the self weight for the pile, which is this one. And then here I'm able to perform a settlement analysis. Now, in this case, you need more time steps because the pile is linear, the soil is linear, but the contact is non-linear. Okay, so now you have a nonlinearity, which is the contact. And keep in mind the contact is a very complicated nonlinearity because it is actually an inequality constraint, and it is quite hard to make it converge. So once again, a transformation. So all the settings are very similar to the previous ones. So static transformation, sparse solver here. Algorithm, the Newton with lens search, same test command, but now I need some more 10 steps. Actually, in this case, 10 is enough because it is not producing a very large vertical displacement. So once again, I keep the load constant. Here it is important because I want to keep the self-weight of the pile constant. And when I'm done with the settlement analysis, I can perform my pushover. So I just need to add, we have a question. Vance, is it possible to add the pile before removing the elements to simulate a wall-stabilized wall excavation for the pile? I tried this on my own, but it crashed, probably only due to the load you mentioned. Yeah, probably it crashed only for the same reason. Of course, you can. You can put the pile here because actually the pile is connected to the nodes on the boundaries, and those nodes are still there. So even before and after excavation. So if you want, you can do it. There is not a problem. You put the pile, you perform the analysis. When you are done with the pile and the settlement analysis, you remove the hole. So it can be done. If you had a crash, the crash was the same probably. When you try to remove the inner elements and the inner nodes, the load was still there, and that load produced a kind of an error. If you want, actually, we can try to simulate it later on. Okay, so I will try just to switch the order of the excavation, and we will see if it works. So after all this vertical analysis is done, okay, I can apply the horizontal load. So the horizontal load will simply contain an instance of the horizontal nodal load applied on the top of the pile. Here the time series is not relevant because actually I'm doing a displacement control analysis. Then I put a monitor here. I put a monitor because I want to monitor the X displacement of the pile head, okay, versus the pseudo time. Versus the pseudo time because since I'm doing a displacement control analysis, the pseudo time is actually the load multiplier, okay? So this one is meters and this one is lambda. Since my reference load was 1000 newtons, this is also actually equal to kilonewton, okay? So it is not different. But here I want to put lambda just to make sure that you understand that it is the load multiplier. After that, I can just perform the horizontal analysis, okay? So the horizontal analysis is all the same settings as before: static, transformation, UMF pack. And then I try to lower a little bit the norm displacement test, but actually you can put 1 to the -7, it's the same, just because I want to make it a little bit faster. The only thing that you have to change now is displacement control. Instead of being a load control, I put a displacement control. Actually, in this case, it is not a problem because you will see that the response is quite linear because everything is linear in my model except of the contact. But when you will go into a nonlinear model, probably you will put also concrete, a nonlinear concrete for the pile. It may happen that you have some kind of softening. So using the displacement control is the way to go. So the selection set will be the pile head, so the node that I want to control. I want to control the displacement in the X direction, and my final displacement will be 0.5 meters. And then I start with 100 10 steps, and then I let the STKO try to adapt the 10 steps if it finds non-convergence. Okay, so this is fine. I can run this analysis. Now I don't want to run it because it takes about 10 minutes. I will show you just the results. But when you're done, you simply measure your model and you run your analysis, okay? In this case, keep in mind that you have to use OpenSees sequential for this kind of analysis. I will show you the output coming from this one. So if I run the monitor, you will see that this analysis took about 11 minutes. It's pretty much linear. It's not exactly linear because the linear will go up to here. There is a small nonlinearity due to contact. But as you can see, for 100 steps, it took about 11 minutes with an average of 10 iterations per step, trying to reach -5. If you want to reach -7, as I said, it will take a little bit more, okay? But anyway, you can try to play with it. So 11 minutes for this kind of analysis, which is sequential. I will show you the results, just to understand what are the all the steps that we created. So webinar soil pile interaction, soil pile custom table. So this one is my model. I want to switch off the grid. I want to go into, okay, that's perfect. So here you can see from the top. Oh, by the way, when you have contact, it's quite important to use a deformation scale of 1. Otherwise, you will see some compenetration, okay? Because with the penalty, you have some small compenetration, but if you increase the deformation scale, this compenetration will be enlarged, so it may seem that you don't have contact. So let's see what happens from above, and then I will show you, I will do a cut, and I will show you step by step what it is doing. So starting from the beginning, you have the first stage of the full soil domain. As you can see, there is not the pile, and the soil domain is full, okay? So you have also this one. I've just done one step here. So stage 1 at time 1 has the full vertical displacement due to self-weight. Then I move to the next stage. I simply created the hole. As you can see now, there is not anymore the feel of the hole. So step 1 of stage 2. Also here, the time has gone once again to 1 because I performed only one step. Now in the next stage, you will see that everything goes up, okay? Now you will see, now I have a displacement of -2 meters. Then I go next, and you will see that now I have the beam, and the displacement has been brought to 0. Actually to 0, but then since this one is the first one with the self-weight of the beam, you see a very small displacement. But as you can see, it went up. But actually, if you look at the stresses, they are still there. So if I visualize the material stress, as you can see, you still have stresses due to vertical weight, okay? Let me go back. As you can see, I have the stress state here, and I still have the same stress state here. So this is the importance of using initial state analysis. You can reset the displacement while keeping the stresses. And then if I go on, now I have 10 steps of vertical displacement. So you can see 0.4, 0.5, the beam is going down, and then horizontal analysis, okay? And the beam will push against the solid, as you can see from here, okay? And you can see the detachment here and the hard contact, normal contact here on this side. Now, if you want to look better what's going on, you can select some of these elements here, you can switch them off, put in a front view, and you can see what's going on here. Okay, so I go back to the beginning. Okay, so the full soil domain, first stage, you have the hole, then you have the pile going back to the initial position by keeping the stresses, then the vertical load of the pile. As you can see now, the stresses, there are displacement, the vertical displacement actually of the pile. Let me show you here. Okay, and then let me show you the vertical displacement. Okay, so you can see the vertical displacement of the pile, and then the pile is bending. Let me go once again to magnitude this time. Okay, and this is basically the way you can where's someone else. This is basically the way you can perform a soil pile interaction, where the only nonlinearity now is the contact. Now, as I said before, if you try to run this model in parallel, you will see some kind of problem. We have another question here from Dennis. What about using brick quad elements in which the self-weight is applied as element force instead of a load pattern? Would that be a solution for the crashing? Of course, yes. Because if you use the self-weight inside the element, there is not a problem, because that self-weight is not putting a load object onto the node. Okay, it's the element itself that produces the right-hand side of the equation. So if you remove the element, you also remove the effect of the load on those elements. The problem is that the elements on the loads on the elements are applied instantaneously, and this is a huge problem when you have contact. Because, for example, if you try to run the vertical analysis, okay, so the self-weight of the pile, with a single step, you will see that it will not converge. Okay, so yes, this is a solution, but on the other side, it is a problem with contact, because with contact, you need to, this will cause you issue with nonlinear solid material model too. That's also true. So in general, I prefer to apply any kind of load in an incremental fashion. The problem is that when you want to apply it as an incremental load, you are forced to apply them on the nodes, and here you have a problem. So if you remove the node, you need also to remove the load on that node, okay? But in any case, if you don't have problem of convergence, this one would be a solution. Okay, so as I said, if you try to run the same model, but with a parallel analysis, it will not perform properly because you have the this piece of code here for the removal, which is created only for sequential analysis. In fact, as you can see here, I'm not doing any check to understand what is the partition, okay? Because for example, here I'm saying remove the element, but now here I'm giving for granted that this element is available on the partition this code will be called, okay? But this is not true because one element is available only on one of many partitions. Okay, so if you have just one partition, or if you do sequential analysis, this code is fine. If you want to use the same code with parallel analysis, it will not work. It will just give error in OpenSees. So you cannot use this one. And what I did actually was to create a new command, which is called remove model subset. Now I will just try to explain you how it works and where you have to put it. And it will be available in the next version of STKO. But in the meantime, for people like Ben said that is doing this kind of analysis, you can simply take this one and copy paste it on the installation folder where you have STKO. So you go, for example, in C, program files, STKO. When you are inside STKO, you go into external solvers, OpenSees, and this one is an analysis step. So you go inside analysis steps. It is a miscellaneous command. So you go under mis commands. And basically, where you have model subset, you also paste remove model subset. If you do this, you will be able to create another subset called, well, after you do this, you need to reload your document, okay? Because if you copy paste that file, when your document is open, you will not be able to see it. But when you create a new document or you close it and you reopen it, you will be able to see it. And it will be under model and under model miscellaneous command, where you had model subset, now you also have remove model subset, okay? Now I will show you just a little bit how it looks like. Well, it looks like this. So basically it's an X object. If you want to understand what is an X object stands for external object. So in STKO, this is the object that connects STKO with OpenSees. And it basically has a couple of methods, two main methods, which are the make X object metadata and write equal. Now, this first method here is used to create the user interface. So let me show you, for example, the model that I used for this one. So if you go under soil pile remove subset sequential, which is the same as this one, but instead of using a custom Tickle script, it is using the new Python feature, which is the remove subset. So as you can see, the model is the same, but instead of creating the two regions, okay, I just remove the load pattern and use the remove model subset. Let's see how it looks like. So these are all the attributes. I have an attribute called remove, and it is an index vector, and an attribute called keep, which is another index vector. Here I have my documentation, and this one corresponds to what I've written into this function. So I first create an attribute metadata. So we have a question here. Another question from Begum. Do the pile nodes and the surrounding soil have to share the same coordinates? No. Oh, actually, thanks for this question, because actually this is a quite important question and I forgot to tell you. So yes, I will explain you this. Actually, they do not have to have the same coordinates, but actually it is better if they do not share the same Z coordinate, because if they do, you have some round-off errors, and sometimes some node may not be in contact with the beam. Okay, so let me explain you a little bit this point. So thank you for reminding this. If I go here and I go in mesh and I go in the front view and I switch off the faces, you will see that now I used a mesh seed of 1 for soil, okay? While for the beam, I couldn't use the same mesh seed, because if I use the same mesh seed, as you can see, this node of the beam will be here. But then there is a problem. Let me do a drawing here. Okay, so imagine this one is my beam. Okay, so I have 2 nodes, and then here my solid at the same location. Okay, now this node here is connected with the nearest element. So I'm saying that this one is the slave and these 2 are the masters. Now what happens is that if they share the same coordinates, it may happen that due to round off error, this one might be at a small tolerance below the minimum coordinate of the pile. And so if this is, now I want to model this kind of tolerance a little bit enlarged, but imagine this is a very small number, like this is 5 and this is 5.00001, or actually 4.999, so a little bit down. This one will not be in contact because it will not find the other beam element, because this one is connected to this beam element, okay? But down here, it will not find any beam, and so it will not find contact, while actually there is another beam element down here. So the trick here is to make the beam element a little bit larger in mesh size, in such a way that, for example, you have something like this, your beam is something like this, in such a way that every node of the soil hits against the segment of the beam. This is quite annoying, and this is one of the reasons why we introduced a new contact element, and I will use the same webinar, now not the next one, but probably the other one. I will repeat the same webinar as today, but using a new element, a new contact element that solves these problems, and it is also always convergent. So we will talk about this later on. So how did I solve this problem? Well, simply assigning a mesh seize at this one, which is about 1.4 probably. But you can play with it just to make sure that every node is connected to 2 beam nodes, not at the same level. So this is quite important. I've seen that if they share the same location, unfortunately, this contact element does not use a tolerance. Okay, so if there are round off errors, it will be a problem. So always try not to use the same location. So one solution, as I did, is to use a mesh seed on the beam, which is quite larger. Otherwise, if you want to use the same beam, the same mesh size, you can take this line, like the line of the beam here, and apply a small translation on top, for example. If you apply a small translation on top and you assign the same mesh size, you will see the mesh, the beam nodes being at the same level plus a small tolerance, okay? And the master node will be the nodes of the soil. No, actually here it is the opposite. The nodes of the soil are the slaves and the master are the beams. This is just because OpenSees has defined this element in this way. So the retained nodes, which are the master node. Oh, actually, by the way, we have always been using the keywords master and slave, but we have seen that in OpenSees they are trying not to use this concept because the slave word recalls the slavery concept. So they're trying not to use master and slave anymore, and we are also trying to follow the same conventions. So now, whenever we say master, we refer to retained nodes, and whenever we say slaves, we will refer to constrained node. Okay. So with time, we will also fix all this kind of terminology. Okay, so going back, so yes, this one is a quite important point. So except from the mesh, the only change I did here, so once you take this file and you copy paste it into your miscellaneous command, into your STKO installation folder, you can go here, you can remove those 3 commands that I used to apply a region, a second region to keep, a region to remove, and the custom TCL script for removing. And you can replace them with this simple command here, which is miscellaneous command, remove model subset. Now here you have to provide selection sets that contain the elements that you want to remove, and the selection sets that contains the nodes that you want to keep. So the same concept as before. I want to remove all the elements and all the nodes which are inside the whole domain, but I want to keep the nodes on the boundary. Okay, and the nodes of the boundary are contained into these two selection sets, whole vertical faces and whole bottom face. Okay, so the concept is the same, and basically here I'm doing the same thing. So I create two selection sets, asking the user to provide selection set for the removal and selection set for the keeping of the boundary nodes. And then I do my computation here. The nice thing is that inside this computation, before writing the TCL script, I check if my model is partitioned. Okay, so I gather all the nodes coming from the selection set to remove. I get all the nodes from the selection set to keep. Then I perform the difference. So I said that all the nodes that I want to remove are the nodes originally defined by the first selection set, if they are not inside the list of nodes that I want to keep. Okay, then here I'm fine. If I'm doing sequential analysis, I simply write all of them. If I'm doing the partition analysis, I write them pieces by pieces. So based on each partition, I write only the element and nodes that are on that partition. Okay, so in this way you will be able to use the same command, but also for parallel analysis. So it is pretty simple. All the other is the same. If you run this analysis, you obtain the exact same result, which is this one. You can launch the monitor. The timing is the same, more or less than 11 minutes. So same response. But the nice thing is that you can convert this model into a parallel one. Now, to convert this model into a parallel one, you can choose between OpenSeesSP and MP. Now, unfortunately, for OpenSeesSP, I will show you how to do it, but this kind of contact elements are not working in OpenSeesSP. Okay, so you may ask, why are you showing us how to do the OpenSeesSP command? Because the new contact elements that we added, and I will show you not in the next webinar, but the other one, also overcomes this problem. So if you want to convert this model to an OpenSeesSP, you simply need to go here, OpenSees parallel SP, and you will see that the model is basically the same. So I have my remove model subset, as you can see. The only changes that I've done is in the analysis. So I go into the analysis. In each and every analysis, when you do the SP, you only need to change the system. Okay, so before I had UMF pack, now you need to choose a solver which is suitable for parallel analysis, and in this case it is the mouse. Okay, but you don't have to change anything else. So the number will remain the same, only the system will change. And also in the displacement control analysis, the only thing that you have to change for OpenSeesSP is the algorithm. Okay, the displacement control is the same. Then once you do these small changes, you go into the analysis, you choose OpenSeesSP. When you choose OpenSeesSP, you can choose the number of processors. So let's say I want 4 processes, and I run this analysis. You will see now the error that will happen with OpenSees. So the first analysis is fine, which is vertical analysis, then the hole, so perform the excavation analysis. Then I put the beam and the contact elements, and then here you will see an error about the MPI channel. This one is basically an error inside the contact element that is not able to communicate between one process and the other. With the new contact elements that I will show you in the next month, this problem will not be there. But fortunately, we can use OpenSees MP to overcome this problem, because this problem is only relative to OpenSeesSP, because OpenSeesSP first tries to build the entire model into one process, then splits the model and sends the different parts to the different processors. And in this process, this element is failing because it's sending a vector of 1, actually sending a vector of 1 while it was expecting to receive a vector of 4. Okay, so there is this inconsistency and it crashes. So that's why now I explained you how to set up an OpenSeesSP model, but for this kind of contact element, you cannot use it. But it will be useful later on with new contact elements, so I will keep it here. Now we'll show you how to do a real parallel analysis with OpenSees MP that works with any kind of elements, so it will be fine. I close this one and I open this one. So subset parallel MP. Now the way you convert a sequential analysis to OpenSees MP is a little bit different. So you first need to change all the algorithms as I did before. Let me pick just one analysis as an example. So you need to change the algorithm, actually, sorry, the system from UMF pack to MUMPS. But in OpenSees MP, you also need to change the number to parallel, okay? These are the only two changes you need to do for every analysis command. And there is an extra change that if you are doing a displacement controlled analysis, you need to switch to parallel displacement control. But by the way, the parameters are the same. So the control node, the control DOF, and the target displacement. The only thing is that you need to move from displacement to parallel displacement control. Okay. So once you are done with these changes, that's fine. You go in analysis, you change to OpenSees MP. When you go to OpenSees MP, you will see that you are not allowed to choose the number of processor. Why? Because in OpenSees MP, you decide the number of processors doing the partition. So since I want to perform an analysis with 4 processors, I create a partition of 4. That's why STKO does not allow me to decide the number of processors, because the number of processors should be consistent with the number of partitions. So once you've done this, you can run your analysis, and in OpenSees MP, you will not see any error. And in fact, here it produced a result. The result is obviously partitioned into many parts. And if I launch the monitor, you will see that it took only 2 minutes, okay, instead of 10 minutes. So here the improvements was a lot. Now you may ask why, if you had 10 minutes and you use 4 processors, why do you have such a speed up? Because now it is 2 seconds divided by 11, so it's much more than 4. The reason is that the MUMPS solver is also much faster than UMF pack. So you have an increase in speed due to parallel analysis, and also an increase in the solution of the linear equations, because the MUMPS solver is already much faster than the UMF pack. So the same analysis that before was 11 minutes now is about 2 minutes. Okay, but the results are the same. And just to make sure that there is no bug and they are giving the same result, I simply copy pasted one of this folder and one of this launcher outside, because if you do this kind of launcher will plot everything on the subdirectories so that you can compare them. So you put multiple plots and you can see that they are all giving the same output. Okay, there is no difference between them. So this is perfect. It works both for sequential and parallel analysis. At the moment, only with OpenSees MP, but as I will show you, there will be a new contact elements that we added, and I will show you in the next webinar how to use it. So that's all for today's webinar. It took a little bit more than expected. I was expecting 1 hour, but it took a little bit more. And if you have any question, oh yes, Bench had a question. He wanted to know if it is possible to switch. Oh, Bench, if you want, you can switch on your microphone so you can guide me through the changes that you wanted to perform. If it is fine for you. Bench, are you there? Okay, so that's perfect, but what is the change? Okay, you can use the chat. What is the change that you wanted to see? It was to add the pile before doing the excavation, right? Okay, so basically I have vertical analysis. Then before doing the removal, I should add the pile and the pile self-weight and the pile settlement analysis before. So I can simply move the add pile after the first vertical analysis. Then the add pile self-weight after the first vertical analysis. Then the pile settlement analysis after the, so I do the vertical analysis of my soil. Oh, there's another question from Begum. Can you please explain about the local axis of the soil? Also, if I want to get stresses and strain at any soil element, the custom command for recorder doesn't work for OpenSees MP, so what should be done? This is quite complicated. Yeah, I will answer this one once we finish this. So, vertical analysis with the soil. Then I add the pile self-weight, I do the pile settlement analysis, then I remove the self-weight from the hole, I remove the hole domain, and I perform the excavation analysis. Now, I need to move the initial state analysis before. So the initial state analysis should be after the vertical. So initial state analysis on, vertical analysis off. Add pile self-weight, pile settlement analysis. Then I remove the self-weight of the soil, I remove the whole domain, I do my excavation analysis. Now my excavation analysis only had one step. Probably here, using one step will not be enough because now there are already contact elements. So probably I will need more number of increments, we will see. We will see highway. Let's see if it works now. Then I have the horizontal load monitor and horizontal analysis. Let's see if it works with the parallel model. So it is already partitioned. Let me run it. Okay, so for a second. Okay, now it is going. Yeah, there is some convergence now error. So probably it is giving some problem, but it tried to adapt the time step. So probably it will manage. Let's see. As you will see, actually, the contact analysis are very sensitive. So you do small changes and it's going to be a mess. So it is actually now struggling in the vertical analysis because probably keeping the whole domain is giving some problem for the contact, but fortunately it's managing. Now, probably I'm afraid that the next step, when you perform the whole, one step will not be enough. And in fact, it is not enough. Okay, so you can try removing the whole now. Before it was a linear analysis, now you have a contact, so probably the excavation analysis should be something like an adaptive time step with at least 10 steps. Let's see. In the meantime, let's answer to, I need to answer to Begum. This one will take a while, this answer, so just let me wait a couple of minutes for this. Anyway. Can we use the new contact element with brick UP element? Yes, you can, because this contact element here, so the beam contact 3D requires 3 dots in the new element. The new contact element actually is already available for any kind of dot set. So it can have just displacement rotation, or displacement pressure. So yes, you will be able to do it. Here is struggling a lot. As you can see, it's trying to remove the time, it's trying to reduce the time step, but it's taking a lot of time. Yeah, we will see, but I don't think it will manage to solve it. As you can see, the norm is quite high and it is not able to reduce it. This actually, probably I know what is the problem here, is that the removal is done in a single shot. As you can see here, let me stop it. Even if I try to reduce the time step, the norm is the same. The norm is the same because even if the time step is very small, This is similar to applying a load in a constant fashion. Even I'm increasing the number of time steps, the element removal is done in a single shot. Okay, so it's like using a constant load. So removing the time step is not doing anything, and this one can be a problem. So for example, in this case, I don't know, probably you can either run a dynamic analysis in this case, so that you remove the elements and there will be some inertia forces in such a way that the soil will go back in place little by little. So you can try to play with it, Benson. I will not save it because let me go back to the, actually I want to open the non-changed MP so that I do not override it for tomorrow. Okay, so you can try to move these pieces as I did, but probably the removal should be done step by step. You can simulate a step-by-step removal, for example, by creating many of these remove model subset and creating several whole domains, okay, pieces by pieces. You can try with 3 or 4 pieces, removing from the top, then to the bottom, probably it will work. But actually, this is a problem because the removal is done in a single shot and you already have soil contact elements there. Probably one solution can be to apply the contact elements after the removal, and before the removal, they can be an equal dot, for example. That can be a solution. You can try to play with it anyway. So first question, yes, the new contact element will be compatible with any kind of offset. Can you explain again the direction local axis we should use if we use a rectangular coordinate, for example? Will it have any difference between the interface at sides or bottom? And this is the same question that was asked by Begum. Okay, so I will answer this question before. Now, the only requirement for this contact element is to know what is the z-axis of the beam, because it already has access to the 2 nodes of the beam, okay? So it is able to define what is the x-axis, okay? So that is fine. Now he needs a z-axis, not because the contact changes, because as you can see, the contact is isotropic, so it's the same. It's not that the contact has one contact force in the z direction and a different contact force in the y direction. It simply needs to understand what is the z-axis, because it needs to pass that z-axis to the coordinate transformation, okay? So it is not important. The only important thing is that the z-axis should never be aligned with the beam. So you can use either a cylindrical local axis like this, or you can use a rectangular local axis. But the problem is that if I use a rectangular local axis here, my default will be with a z-axis. Oh, actually, this is a cylindrical one. Let me create a rectangular local axis. By default, it will have a z-axis applied on top. So this one will not work because in this case, the z-axis is aligned with the beam. So I can either go like this and create a local axis here. This one will be fine, okay? Because now I have a local axis that points not in the same direction of the beam. So this one is fine, okay? The only reason why I wanted to use this one is that it is easier to create because by default, it applies the z-axis in the outward direction, okay? So this is the only reason why I used the cylindrical. If you want to use the rectangular one, you need to change the default view to a front view, because in the default XY plane, the z-axis is aligned with the pile, okay? In this simple example. Okay, so we have another question. Oh, then I still have to answer. So this one for the local axis is answered. I need to answer to this one. If I want to get the stresses and strain at any soil element, the custom command for recorded doesn't work for OpenSees MP. So what should be done in this case? If you're using STKO, as I imagine, there is no problem, because if you go in STKO, you can actually, oops, yeah, this is fine. You can use a surface color map. If you just want to visualize them, you can use material stress here, and you have all the stresses. Then you have all the different components, and you also have the invariance, the stress invariance. Then, if instead you need some output file that summarizes all the stresses of every element, you can use the script editor. We have shown in the previous webinar, not the previous one because it was on parametric analysis, but the very first one, I showed how to query the output database to get the stresses or displacements or reaction at any points in the domain. Okay, so you can simply develop a script that takes the results from the MPCO output and creates a report text file for you. Okay, the problem is that yes, if you want to use a record, a standard OpenSees record with OpenSees MP, will be a mess. Will be a mess because you have to create the same record for each process, and you have to know, if you want to record a stress on a certain element, you need to know what is the partition of that element. And that is not easy. So yes, I would suggest you to use the MPCO recorder and the Python API. So we have one extra question from Wairobo. Is it possible to add a dynamic loading to the bottom of soil domain by using Lesmer-Kuhlemaier and connecting it with the same soil instead of a hard rock? Referring to the previous webinar on soil structure interaction. Yes, I mean, in the previous webinar of soil structure interaction, I used the Lesmer-Kuhlemaier properties of a bedrock. If you want to use the Lesmer-Kuhlemaier property of the same domain, so if, for example, if you don't do a cut at the level of the bedrock, but there is the same soil domain, even in the part that you didn't model, you simply apply the Lesmer-Kuhlemaier related to the velocities of this soil medium. Okay, so that is the same. You simply have to change the Lesmer-Kuhlemaier properties. Okay, so next question from Yue. Will we need to compile our OpenSees MP if we want to use the new contact element in the future? Yes, the new contact element actually has been already tested by us, and we are going to send it to the official OpenSees repository in the next days. So yes, if you use your own OpenSees MP to your high-performance computers, you will have to download the new source code and recompile it. Of course, because that element has been added to OpenSees. It's not just an STKO automation. It's actually in the OpenSees source code. It will be called zero-length implex contact, and I will show you in the next webinar how it can be used. Another question from Ben's OpenSees has a friction off on command for the contact element. This can be great for analysis where the part is considered wished in place. How is this implemented? It simply set mu 0 and doesn't modify cohesion. No observation, it doesn't turn off cohesion for being contact element. No, friction on off, simply, yeah, it's like setting mu to 0 and then resetting mu to the real value. But the cohesion is another thing. Cohesion is like adding a constant value to the value coming from the cohesion, the value coming from the friction. So the equation was something like, so the critical tau, actually the critical tau would be minus mu times the sigma n only if n is negative. Okay, so if there is pressure, the critical tau will be this one, and basically it corresponds to the cone here. Okay, so when the sigma n is negative, I have this equation, otherwise it is 0. Okay, when you add cohesion, it is simply doing this one plus C. Okay, so it's just adding an extra value here. Then plus C, but actually this C you have to remove some place, otherwise it's like this one. So it goes down like this. So that's why if you turn off this one, mu to 0, it's like using this kind of surface. So the cohesion will always be there. Because actually the cohesion has nothing to do with friction itself. The cohesion is like an extra shear strength of the medium in between the two contact bodies, okay? But in my opinion, you should not use it, because the cohesion makes sense only if you have your pile here, then you have your soil here, and here you have some kind of cohesion element that has a cohesion. But actually, if you want to simulate a non-perfect contact surface, that can be useful too. But yes, if you want to switch off and on friction, you will switch on and off this one, I think. For clays and solid soil, it can be important at the contact. Yeah, the problem is that I don't know if you can change it. Actually, let me look inside the source code, because probably you can change the cohesion using the set parameter. Okay, so let me just have a look at the beam contact. Actually, it's contact material. It's contact material 3D. C++. Contact material 3D. If you are lucky, there is a set parameter command. And these are the parameters that you can change. Nothing. Okay, so you're not so lucky. You cannot change. You can just change the frictional coefficient, as you said, but unfortunately they didn't update it to the set parameter command here. So if you switch the frictional contact, they just change to 0. No, they set the equation to 0 actually. So if you switch off friction, they set the equation to 0. They set the tensile strength to 0 and the friction coefficient to 0. So it should be fine. So actually you were saying that doesn't modify cohesion, but it seems that it does. Try to do it with the new version. Probably there was a bug in the previous version, but now it looks like it is changing cohesion to 0. Okay, so you try to do the same analysis, but with the latest version of OpenSees. Now, I don't know if they change it right now. Comes from the load problem, like everything in that's a problem. Yes, that can be a problem. Okay, is there any other question? Some doubts, something that you want that is not so clear? Oh, you're welcome. You're welcome. And actually, this one is the first webinar on soil pile interaction. As I said, the next webinar will be on a very nice topic, actually. And then the next webinar, so after the next one, I will repeat the same as this one. So soil pile interaction using the new contact elements, because actually now we've added in OpenSees 2 nice elements. One contact element that is able to be oriented in any direction. And there is also Dennis here. Dennis implemented this element, and then I helped him just a little bit. And the nice thing of this contact element is that it is always convergent, because it uses a particular kind of integration scheme that makes the analysis stepwise linear. Because actually what you will see is that now I set up the contact parameters and the time steps in such a way that this model converges, but you will see that contact is very, very unstable. In fact, as you can see, if I just move the contact before the excavation, the program couldn't find any convergence. So it is actually a mess. And that new contact element will be very useful. Other than this, we've added a new element, which is used to embed an element inside another. So it will be very useful for doing micro modeling of concrete structure, but also to attach incompatible meshes. And this will be the topic of the next webinar. We have another question. Oh, local access of the soil. Yes, I forgot to answer to this question of Begum. What are the local access of the soil? Actually, OpenSees does not ask for any local access on the soil. The only local access I gave was for the beam and for the contact elements. Because in a beam, it is mandatory to assign a local access, because the only known direction is the actual direction of the beam. But in order to orient the cross section, you need to know also the Y and Z axis. Now, for the soil domain, there is no need to give a local axis because they already have by default the global local axis, which is the one that OpenSees has. So if you look inside the soil domain, they all have the X, Y, Z axis aligned with the global one. That's why you don't need it. There is an opportunity in STKO to assign a different local axis also to soil, but just for visualizing stresses in a different orientation. The problem is that you will never need to visualize stresses in a different orientation rather than the global coordinate system for solids, okay? Well, unless, for example, you are modeling a slab with solid elements and you want to see the stresses aligned with the principal directions of the slab, then in that case, you can assign a local axis, but that will only be used by the post processor to orient the stresses in the new local direction, okay? So it will have nothing to do with the analysis. So if this was your doubt. But as I said, in this example, I didn't use any local axis for solids. Oh, you're welcome to everyone. And thank you, Dennis, for the implex element. And Dennis is the guy that implemented the implex element. And Dennis, we will introduce your implex element on this same example, not in the next webinar, but the next one again. Okay, so next webinar will be, he's not here. Why is, no, Dennis is here, he's on YouTube. Yes. Okay, so thank you very much to everyone. If there is no other question, yeah, he was too lazy. If there is no other question, once again, thank you everyone, and see you on the next webinar. By tomorrow, we will put all the models and the video recordings on our website. And yes, feel free to ask anything on our forum if something is not clear or if you cannot reproduce the same results, because if you change something in this model, you will see what is the real problem of contact elements. They are really sensitive to small changes. So you change something, even the material parameters, and probably you will see that you don't have convergence with those contact elements. So try to play with them, and if you have doubts, write on our forum. Okay? So thank you, everyone.